Okay, thank you for everyone to attend to come for the seminar today. It's my great honor to introduce Dr. Sushant Mahajan. Dr. Sushant Mahajan is a postdoc from Institute for Astronomy, University of Hawaii at Manoa. He received a PhD from Georgia State University in 2019, and he will join Stanford in January next year. He has over 7 years of experience in creating physics-based numerical simulations and 2 years of experience in working with machine learning to mine for patterns, which can be used in forecasting solar flares and space weather. He also studies solar surface flows by correlation tracking method and local heliosseismology. He is a part of our Surface Link team in our COFFIES Center. Let's welcome Sushant again and let him start the seminar.
All right. Thank you for having me here. I was kind of in a dilemma in creating this first slide because the work that I'm going to present here today, I've done that when I was at Georgia State during my PhD, but right now I'm at the Institute for Astronomy working with Sushant. So I still decided to put the IFA logo on here. All right. So this is about correlation tracking measurements. I got into local helioseismic measurements later during my postdoc, but the work that I'll be presenting today is about correlation tracking on solar magnetograms. All right, so we have 411 plus years of sunspot numbers recorded since the time of Galileo. It's one of the longest regularly maintained data set in astronomy. And we know that the sunspot number waxes and wanes in cycles of 11 years, roughly. And if you look at the butterfly diagram down here, we know that sunspots at the beginning of the cycle start appearing at higher latitudes. And as solar cycle moves on, as sunspot numbers start increasing, newer and newer sunspots start appearing at lower latitudes. And while these sunspots are emerging, the magnetic field in sunspots decays over the solar surface, and some of it gets transported towards the poles, where you see inversion in the polar field near the sunspot maximum. So these are kind of out of phase cycles, the sunspot number waxing and waning and the inversion of polar field on the solar surface. Now there are certain, all of this happens with certain empirical laws. In 1919, George Ellery Hale and Joy made this observation that there's a significant amount of magnetic field, first of all, in sunspots through Zeeman splitting. The magnetic field can be 1,000 to 2,000 Gauss in strength, and that almost all sunspots appear in pairs, or sunspot groups appear in pairs of opposite polarity spots. And these bipolar magnetic regions, as we call these pairs of sunspots, appear with tilt with respect to the east-west direction on the surface of the sun. And that tilt is proportional to the latitude of emergence. So the bipolar magnetic regions appearing at higher latitudes tend to have a higher tilt than the regions appearing closer to the equator. Later in 1955, Eugene Parker proposed magnetic buoyancy as the cause for sunspot emergence. What he basically proposed was, if you have a strong enough magnetic field inside the sun in the form of a cylindrical flux tube, the gas density inside the flux tube would be lower than outside the flux tube if the flux tube was assumed to be in isothermal equilibrium with its surroundings. And this lower density inside the flux tube makes the flux tube buoyant, where it can rise to the surface and pierce the photosphere at two locations, creating sunspots of opposite polarities. So he proposed magnetic buoyancy as an explanation for how sun spectrums form. One of the other observational constraints we have is differential rotation inside the sun. So the sun is a big hot ball of plasma that does not rotate exactly like a rigid body. It rotates differentially. These are measurements from global helioseismology, which is a study of the propagation of sound waves inside the sun that allows us to invert the sound wave travel time measurements into plasma flow velocities inside the sun. And you see that the equator of the sun, which is here, rotates faster than the poles. And this rotation rate not only varies with latitude, but also with depth. The red dots here indicate the region between the radiative zone in the interior and the convective envelope. That region is called the tachocline, and it is usually defined as a high shear region where the differential rotation changes more rapidly. And on the right, you can see another flow profile that we know for sure exists on the surface of the sun, where a weak meridional flow transports magnetic flux from the equator towards the poles at the surface, and it is supposed to return back towards the equator at some depth below the surface. But the depth of this return flow is argued, as well as the nature of the cells of meridional flow, whether it is a single cell or it's a multiple cell structure, is still kind of debatable. So how do you put all of this together? Let's try and build up a cartoon picture of the dynamo. So if you start inside the sun with a magnetic field pointed from south to the north, and there's differential rotation inside the sun where the equator is rotating faster than the poles, is because magnetic flux is frozen in the plasma inside the sun. This poloidal magnetic field pointed from south to north will start getting stretched and wrapped around the sun because of this latitudinal shear in differential rotation. Once you've, and in this process, that magnetic field also gets amplified as it extracts some kinetic energy from plasma motions and converts it into magnetic energy. Once you have a strong enough magnetic flux tubes inside the sun, they can be subject to magnetic buoyancy and rise up to the surface, pierce the surface in two locations, creating bipolar magnetic regions. While these flux tubes are rising through the convection zone, because they are on a rotating body, they're subject to Coriolis force, which imparts a tilt, the Joyce law tilt that we saw earlier, to these bipolar magnetic regions. And the tilt is such that the polarity of spots that ends up closer to the poles has a magnetic polarity that's opposite to the polar field at the poles. Over time, through diffusive processes, if you cancel some of the magnetic field in the spots in opposite hemispheres that are closer to the equator, you end up imparting end up with some magnetic flux remaining from the polarities that are closer to the poles. And meridional flow on the surface will transport this remaining magnetic flux to the poles to invert the polar field there. And you end up with a magnetic field that is opposite to the direction you started with. All right, so on what happens after the emergence of sunspot groups, how the magnetic field decays, is modeled in something called surface flux transport simulations. What they are is basically if you know the velocity fields on the surface of the sun, you can move around the magnetic fields that has emerged on the surface by either modeling it in the form of artificial sunspots or by assimilating solar data from solar magnetograms directly into your model and moving the flux around. Surface flux transport simulations are shown to be pretty useful in predicting what the polar field would look like at the end of a cycle if you know which sunspots are going to emerge and where they're going to emerge and when they're going to emerge. So it is really important to characterize and know what kind of velocity fields there are at the surface if we want to fine-tune these surface flux transport simulations to better model the surface of the sun. Okay, so if you want to measure the meridional flow at the surface of the sun, which has a peak amplitude of nearly 15 meters per second at mid latitudes, and it decays above and below the mid latitudes. You need an accuracy around 0.5 meter per second to 1 meter per second. This is equivalent to tracking something that moves by the width of a human hair in Atlanta while you're sitting in Hawaii in 1 second. So the accuracy is really incredible. And there have been studies in the past which have used correlation tracking on solar magnetograms to measure meridional flow and differential rotation, like Com, Howard, and Harvey in 1993, and Lisa Upton and David Hathaway. And their accuracy has been to around 3 to 4 meters per second, as I'll show later. All right, so this is a typical magnetogram. White color here is represents positive magnetic field. Black color here represents negative magnetic field. And the Earth is shown to scale here. You can see bipolar magnetic regions with opposite polarity groups of spots, and with a tilt with respect to the east-west axis here, right? So what we're tracking in the study is not the sunspots themselves, because the sunspots are really large magnetic features, and their magnetic fields can be anchored much below the photosphere. So they would move around with velocities in deeper layers inside the sun. We don't want that. What we want to do is track how the small scale magnetic elements and the network of these small scale magnetic elements moves on the surface. So what we do is we actually mask out active regions, and what we're trying to track are these inter-supergranular lanes where these small scale magnetic elements accumulate around the boundaries of supergranules where there are converging flows. So this is what a typical movie of a magnetogram looks like. Left to right here is longitude, and vertical axis is latitude. The white regions that have no data are the sunspots that were masked. And you can see that that over several hours, the large-scale magnetic network kind of stays coherent, which means you can track the speed at which this network is moving. All right, so this is just a coarse version of the grid that we're using. First of all, we take the solar magnetogram and we project it into a heliographic projection, where equal number of pixels equals equal number of degrees in latitude and longitude. What that does is it does stretch out the limbs of the sun, but we try to account for that stretching when we interpolate this data. We also split each latitude into several blocks in longitude. And the overall goal is to, once you select a block from this magnetogram, and then you look at another magnetogram a certain time apart, what you're trying to do is trying to see where this block has moved by cross-correlating over a search area and trying to find the maximum correlation coefficient. So this is on the right what a typical correlation coefficient looks like as a function of the shift in the horizontal direction and the vertical direction. What we're essentially trying to do is trying to find where this correlation coefficient peaks to find out the most probable velocity at which a particular block has moved. Now, I started working on Lisa Upton and David Hathaway's algorithm, which was already existing, and found several things that needed improvement. So this talk is really about discussing those improvements that we made. The first was peak locking. So if you plot a histogram of all the velocity measurements measured over a Carrington rotation in terms of meridional flow, you would expect to get a Gaussian-like profile, but what you get are this spiky profile where each of these peaks are separated by 18 meters per second. If you're using an 8-hour gap between two successive magnetograms when you're tracking. If you're using a 24-hour gap between two magnetograms, these pikes are spaced at 6 meters per second. What this is called peak locking in the field of particle image velocimetry. Particle image velocimetry is where they study flows around airplanes and jets in wind tunnels by introducing luminescent particles in the air and tracking those particles. So they struggle with this effect as well. This is an effect of resolution and how we detect the peak of the cross correlation coefficient by fitting a parabola or a Gaussian to that peak. And that peak is biased towards giving us more number of measurements that are at integer pixel shifts than at fractional pixel shifts. So you would have more measurements at exactly 1, 2, 3 pixel shifts rather than 1.5, 2.5, and 3.5 pixel shifts. And this is a very common bias in correlation tracking, but we found that it wasn't addressed in literature in solar physics. So we decided to address it and suggest a solution for it. This bias usually is around 0.1 pixel. And if you're looking at 8-hour time lags, 0.1 pixel bias means 1.8 meters per second. That's significant. If you're looking at a 1-hour lag, then the 0.1 pixel bias can completely blow your meridional flow or overpower your meridional flow. So we thought it was important to address this. What we did was we implemented an iterative procedure to converge to the actual peak of the correlation coefficient, which made these histograms smoother and improved the accuracy 5-fold. All right, one of the other things we did was we expanded the search area as you went to higher latitudes to correspond to the same physical distance in terms of searching for the for where the block has moved, instead of keeping it constant in terms of longitude, because if you don't expand the search area as you go up towards the limbs, you can cut off the tails of your distribution, which could make the mean of the distribution biased on one side of or the other. So on the left is what the histograms looked like before, and on the right is what the histogram of meridional flow measurements looks like after making these two updates. One of the other things we did was we created a pipeline to test any kind of tracking algorithm with synthetic data. What you're seeing here is a movie of synthetic images that we produced. So these images are produced with an analytical formula, which places a two-dimensional Gaussian distribution of magnetic field or any quantity you want on the surface of the sun. And because this is an analytical formula, you can sample this at any resolution you want by passing it through a CCD emulator. Because it's an analytical formula, you can move any of these features with a precise displacement or velocity and use that to calibrate your tracking algorithm. So here's what the projection of one of the synthetic maps that we produced looks like on the grid that we are using, and you can clearly see stretching of the features as we go towards the limb. So one of the other updates we made was to the interpolation that we use when we project onto a heliographic plane. So on the top left is what a feature in a synthetic image looks like at 60 degrees latitude and 60 degrees longitude. So it's in the north east, near the northeast limb of the sun, when sampled at high resolution. If you sample the same feature at lower resolution, it'll look like it's stretched in a direction away from this center, right? Okay, now if you want to test the interpolation algorithm that you're using to interpolate when you're projecting the solar disk onto a heliographic map, what we did was we tried different interpolation algorithms to upsample this low resolution image and see if we could reproduce the high resolution image of what the feature should look like. If you use a simple cubic interpolation over image pixels, where each pixel is not equidistant on the surface of the sun because the sun is curved, you end up with a feature that's stretched in a direction away from this center. And the shapes of the features are important because the shape of the feature will basically decide what the shape of the cross-correlation coefficient is going to be. If the features are Gaussian, the cross-correlation coefficient will be Gaussian. If the features are stretched in one direction, the cross-correlation coefficient will be stretched in that direction and might bias your results and create a kind of shift away or towards the center in this case. The other interpolation we used was spline interpolation to oversample this low resolution image. And it doesn't look like the high resolution image at all. It's still stretched in a direction away from the center. So then what we decided to use was a more computationally expensive, but a bit more accurate procedure that was proposed by Sandwell in 1987. This is a scattered interpolant. It takes into account the actual distances between pixels because they aren't equidistant on the solar image. If you take into account the actual distances between pixels and relative to where you want data from, you end up with slightly less biased, less stretched out feature. It is still more diffuse than the high resolution feature that you want, but just diffusion shouldn't impact our results that much because we're just tracking the location of the feature. What we want is the center of mass not to change. And the center of mass was going a little bit away from the center in when we were using interpolation over the pixel grid, the image grid. When we use this scatter interpolation, it makes our higher latitude and near the limb measurements more accurate because it doesn't stretch features as much. All right, so finally, after making these improvements, when we ran the code on solar magnetograms, what we found was another kind of bias. So on the top left here is when we were tracking magnetograms. And if you subtract the average rotation rate at each latitude, you get this kind of a residual, which suggests that the east limb of the sun is rotating slower than the west limb of the sun. This is clearly a bias because the sun doesn't know which central meridian we're staring at and cannot adjust its rotation rate accordingly. If you look at the residual rotation rate at the equator, you can see this near equator flow is around 100 meters per second slower on the east limb than on the west limb. In terms of meridional flow, there wasn't an east-west bias, but as we increased the lag between two successive magnetograms when we're tracking, for the shorter time lags, we got a very high meridional flow. And as we increase the time lags, the meridional flow kind of decreases and settles into this nearly sinusoidal profile. Now, this was very weird to us because we expected meridional flow or rotation rate to be nearly the same, no matter what time lag you use between magnetograms. We expected some differences, but not this much. This is like threefold difference. So there was clearly something going on. When we used unsigned magnetograms to do tracking, this east-west asymmetry in the rotation rate measurements reduced to half its previous amplitude, but there was still differences in terms of variation with time lag. They were just not as pronounced as they were on the signed magnetograms. And to make sure that it's not our projection or the algorithm, tracking algorithm, that is creating this kind of a systematic error, we ran our algorithm on the synthetic magnetograms that we created using the analytical magnetogram creator. And we don't see any east-west biases, and we barely see any differences in the meridional flow profile with time lag when we run on synthetic magnetograms. So we don't believe it's something coming from tracking algorithm. It must be something that's inherent in the data. Okay. Other studies have reported similar results, like Swami's, which is a code that tracks individual magnetic features based on their center of mass. And Derek Lamb in 2017 reported a similar very high meridional flow for feature lifetimes of 2 hours or less. And when he tracked features that lived longer, like 8 hours, he got a nearly sinusoidal meridional flow profile. So it wasn't just us. Even Loptin et al. In 2017 got similar results. They published a paper calling it the shrinking sun effect, although their bias was in the opposite direction. Their systematic bias was something that was like a pseudo flow pointing towards this center, whereas what we see here is supporting differential rotation on the right and going against rotation on the left. So what we're seeing is like a pseudo flow away from this center. All right. So what is happening? If you look at the total displacement that we measure typically at 60 degrees latitude in the south to north direction as a function of time lag, you start with around 65 kilometers for the first hour, and then at 2 hours, you expect this displacement, if the velocity is constant, nearly constant, you expect this displacement to double, but it doesn't. It just increases by like 20% or so. And then it plateaus as you go to longer time lags. So what is going on here? What we tried to do was decompose the displacement into two quantities at first. A true velocity, a baseline velocity, and a systematic error. Assuming that the true velocity and the systematic error would be independent of time lag, we try to solve for them using different combinations of measurements at time lags. So what we do is run the tracking at 1 hour lag, run the tracking at 4 hour lags, 2 hour lags, and 8 hour lags, and calculate this baseline velocity and the systematic error. But they came out to be different as a function of time lag. So we introduced another quadratic term, which allows the velocity profiles to change a little bit, because we do expect some change in velocity profiles as we track features that live longer at longer time lags. They could be anchored deeper inside the sun and could rotate or move with a different velocity. So when we introduce this quadratic procedure, now we have three unknowns. So to solve for all these three unknowns, the baseline velocity, the quadratic term, and the systematic error, we needed measurements from three different time lags, which was 1, 2, 4, and 2, 4, 8 hour time lags. And when we decompose these three quantities, they came out to be pretty similar, no matter what combination of time lags you used up until 8 hours. So that kind of validated our assumption that these three quantities are independent of time lag. This assumption isn't true, though. If you go past 8 hour time lags, then things start to change. But up until an 8 hour time lag, you can decompose the displacement into these three quantities. Now, the first plot on the left is the baseline meridional flow profile. It looks nice and like other studies have shown before. And in the middle panel is the capital delta. That's the systematic error. This is like a constant shift in terms of kilometers. So at 60 degrees latitude, it looks like there's always a 50 kilometer shift, no matter what time lag you're looking at. Even if you were looking at a zero time lag, you would still see a 50 kilometer shift. And on the right panel is the quadratic term. This is like an acceleration term, which changes the flow profiles by a bit. This is around 0.3 meters per second per hour. So what it is saying is that for every hour of time lag that you increase between successive magnetograms, the meridional flow would decay by 0.3 meters per second. All right, so what this decomposition gives us is, like, on the right, you see the total displacement again, but yellow component is the systematic shift. That's the center to limb effect that is always there, no matter what time lag you look at. And the blue part is the non-center to limb effect part, which includes the baseline velocity as well as the quadratic term. And if you break down that blue part into this blue and red, the blue here is the baseline velocity. So the displacement due to the baseline velocity just linearly increases in time because the baseline velocity is constant. And the quadratic term contributes more and more towards the longer time lags. So at shorter time lags, you're really affected by the center to limb effect because it moves things by 50 kilometers. And at much longer time lags, you're affected by the quadratic term, which contaminates your velocity measurements. What you truly want, the baseline velocity is the displacement that's shown in blue. Okay, so here are our final measurements. On the top left panel is the meridional flow for the past 2 cycles, both the MDI era from 1996 to 2010, and during the HMI era from 2010 onwards. On the right, top right, is the torsional oscillation profile for the same 2 cycles. And you can see solar cycle variation in the meridional flow profile here, where the meridional flow is slower during sunspot maximum, and it picks up in amplitude during the sunspot minimum. What you should note here that I haven't cross-calibrated the baseline velocities, neither the meridional flow nor the torsional oscillation across MDI and HMI. And although you can see some sharp change around 2010 when we switched from MDI to HMI at high latitudes, at low latitudes, you can barely notice any difference when MDI switches to HMI. So most of the difference between MDI and HMI was actually captured by the systematic center to limb error, which changes drastically between MDI and HMI, making the true baseline velocities nearly consistent, which kind of increased our confidence in this procedure, because that was not something that we were expecting to just come out. The bottom panels are the quadratic term, where the quadratic term is negative in the northern hemisphere, which is opposite in sign to the meridional flow in the northern hemisphere. So it is suggesting that the meridional flow will decay as a function of time lag. As you track deeper and deeper layers of the sun, the meridional flow, you expect it to decay. The last panel at the bottom is the Legendre coefficients fitted to the baseline meridional flow velocity, which are a proxy for the amplitude of the meridional flow. And in white is the sunspot number, which shows that the meridional flow amplitude is anti-correlated to the sunspot cycle. All right, here's, if you wanted to see in detail what the overlap period during for MDI and HMI looked like, here's the baseline meridional flow velocity obtained during the overlap period on the left, and the rotation rate on the right in Carrington frame of reference. You can see that within 45 to 50 degrees latitude, the meridional flow velocity pretty much agrees across MDI and HMI. At high latitudes, MDI does some weird stuff, which I don't really believe. I would trust HMI measurements at higher latitudes because it's the more like high resolution instrument. So at high latitudes, there are significant differences, but at latitudes where you can trust both instruments, they pretty much agree with each other, and you don't need to cross calibrate because most of the differences between the instruments were automatically and fortunately captured by the center to limb effect. The rotation rate is similar across both instruments. There are some differences very close to the equator, but they aren't very significant to say that these profiles are truly different. All right, so what did we find about the center to limb effect? First, if you look at time lags below 1 hour, we tried experimenting with 45 seconds, 12 minutes, 24 minutes, and so on. The center to limb effect builds up in time over the first hour of time lag, and then it stays constant from 1 hour time lag and above. Because the center to limb effect is like a constant shift, its contribution to the velocity, when you divide that constant shift with the time lag, its contribution to the velocity decreases in time. But as you go farther in time lags, the quadratic term starts to contribute more. And the center to limb effect may depend on magnetic field strength. As we see here, the constant shift error is kind of lower within the wings of the butterfly and higher outside. So there may be a magnetic field dependence of the center to limb effect. This is something similar to what Loptin et al. In 2017 reported. They also think the center to limb effect is dependent on magnetic field strength. It is nearly identical in the east-west and north-south direction. So this is something that we've that has been assumed in previous studies where people like measure the asymmetry in rotation rate across the central meridian at the equator and use that to correct for the center to limb effect in the north-south direction by just assuming that it's identical in both the directions. Our analysis doesn't assume that, but we found that it is identical in both the directions because we do our corrections over the entire disk without any longitudinal averaging. All right, all these measurements are available for download. If you look up our paper that was published in 2020, sorry, I forgot to include the links here. It's available on Harvard Dataverse. If you just search for LCT, local correlation tracking on solar magnetograms in Harvard Dataverse, you can download the data that is required to produce all these figures. That's it. Thank you. If you have any questions.
I have a question.
Uh-huh.
On the slide you showed for the comparison with MDI, on the right-hand panel, showing the rotation rate.
Mm-hmm.
On the higher resolution instrument, there's a dip at the equator.
Yeah.
Bob Howard saw that all the time on the Mount Wilson Dopplergrams, where he was able to use the same instrument for every pixel, unlike something like MDI or HMI, where you have a different instrument for each pixel, because the wavelength passbands are not uniform across the field. So it's difficult to see things like that. That's why we use seismology instead of Dopplergrams, direct Dopplergrams. But it's interesting that the slowdown at the equator was there in all the Mount Wilson data also. So do you believe that is really showing something here that's real?
Yeah, it could very well be, but the confusing part about it is why would MDI not show that and HMI would catch that during the same time period.
Yeah, it's just curious.
Is the ground data too? But does anybody have any idea?
Well, the ground data is what I was talking about, the Mount Wilson data.
No, I'm saying GOG. Global
Oh,
observation rate to GOG data.
well, GONG will have some of the same kinds of problems that MDI and HMI have, where there's slight differences across the field of view in the central pass bands in the profiles. So it's difficult to use direct Doppler for these filtergram instruments.
I have a question about the Senatolem effect. I'm thinking or guessing how the systematic effect is related to the measurement time, and I'm just guessing wildly that could it be related to distance? Because the longer the time, the larger the distance in the correlation tracking.
Yeah, so if that's one of the things that I've wondered, and one of the motivations behind us using or updating our interpolation technique, because if you're tracking a feature that is moving across the disk large distances, and it will change its shape, when you project it, like if it's going from near this center to near the limb, and you're projecting it into a heliographic coordinate system, it will look different. Even though it's supposed to look similar, it'll look different, because the near the limb it'll get more stretched, which is why we updated the interpolation method to correct for that, and we still see center to limb effect after that. So I don't think at this point we that it's because of the increasing displacement that we see. Plus, at 8-hour lags, the displacement isn't that much. It's 1/3 of 14 degrees, so it's about 5 degrees in longitude.
Okay. How big is the Senatolem in your method? Like in meter per second, or like equivalent to meter per second or seconds?
In terms of kilometers, it goes from like 50 kilometers on the east limb to 50 kilometers on the west limb, and then you can divide it by whatever time lag you use to see how much it impacts the velocity.
Thank you. Yeah, I'm just thinking how physically it could be related to time. Thank you.
On a different scale, on the WSO scale, where the pixels are 3 arc-minutes instead of, we found that the limb darkening across a quote pixel is obviously significant, and that we use what we call an effective position for each pixel. And it's always displaced toward disk center because it's brighter there, and you're actually seeing where the light comes from in each pixel. So there's a bias toward the center, and that bias out toward the limb was about 1/3 of a pixel. And we played with different sizes, and it seemed to be the same fraction at different sizes of pixels. So I wonder if that is part of this, few kilometer difference that you see toward the limb. On the average, it's brighter toward the center. Have you ever thought about doing a correction of the position of the pixels biased by the darkening. It should be tiny.
That is very interesting. So here, I think in our case, 1 pixel for HMI is about half a megameter. So this kind of shift is 0.1 pixel.
Yeah, so it could be there. But of course, yeah, it's interesting to see on average over a long time how that works.
Yeah, definitely.
I have a couple questions. Yeah. So I know you said that you actually started with Lisa and Dave's like initial work that they were doing. So this might be something that they set, but in terms of when you're thresholding out or like masking out the active region or the strong magnetic field, what threshold are you using for that? And how do you go about deciding what that threshold is? Like what's too high and what's good enough, I guess.
So the threshold that they'd set was 150 Gauss. The only kind of modification I made to that was I made it to be consistent in terms of average magnetic flux over several pixels in MDI and HMI. So what I do is I choose a 9x9 pixel area in HMI, and if the average magnetic field in that 9x9 pixel area is about 150 Gauss, then we mask the center pixel. And for MDI, we do it over a 3x3 area.
Okay, yeah. And I'm assuming that's a shifting average. So you're not, like you said, it's the center pixel, but that information still goes into whatever, the one to the left of it if the average isn't too high.
Yeah, and we just confirmed it visually. It looked good enough for us to exclude major parts of the activity.
My other question is, so I think it looks really good that you've changed the interpolation to correct for the shifting based on where things are on the disk. And I know that you said that the diffusion that seems like it's happening with the 4x4 pixel interpolation doesn't really affect your results that much, but it seems like that should still be somewhat dependent on disk location. And is there a way to kind of extrapolate down or scale down, figure out what the diffusion is based on disk location, and then account for it in that way, so that if people do care about the strength of the field, that it can be accounted for there?
From the amount of information that exists in the magnetograms, I don't think it's possible. What we would need to know, I think, would be the filling factor if we wanted to reproduce the shape accurately, because like this low resolution image is like 4 or 5 pixels by 5 pixels, and this high resolution image is like 21 pixels by 21 pixels. So to reproduce this from this, there just like isn't enough information to accurately get the size as well, because in this low resolution image, you don't know what the filling factor is, like how much area actually the magnetic field is occupying. So you end up conserving the flux nearly, but you end up spreading it over a larger area because you had a low resolution image, and you assume that magnetic field is like constant throughout the pixel. We don't know the detailed structure inside. But because, so what this does, this diffusion is here. On the right is the correlation coefficient and we're trying to find out where the peak is, right? If the features are more spread out, it'll just broaden this correlation coefficient and shouldn't affect the location of its peak per se. So for our purpose, it's not something that we need to worry about. But I suppose if you're doing something else, you might need to worry about that. Yes, Phil.
You're muted.
You're
Phil.
muted, Phil.
Muted. Should be muted. HMI has a variation in measured field with 24 hours and 12 hours due to the orbit. Do you see any 24 or 12-hour power in the number of pixels that you eliminate?
We might, but all the measurements and this decomposition of the displacement into these three components, all of this is done over a Carrington rotation averages. So we haven't really looked into what small scale variations there could be. Everything we do is averaged over Carrington rotations first.
That could put a little bit of a bias in.
Yeah, true. You might have to investigate that.
Yeah, just curious. Okay, this is great stuff. I like it.
Thank you.
Any more questions? Okay, yes, exactly 1 hour. Thanks to Sushant again for the wonderful presentation and great work.